Hi, everyone. Welcome back to IPAC 2026. Brendan is going to continue to tell us their really nice result on the proof of the fuse conjecture.
All right. Well, thank you very much, Anna. I'm going to move on today to the last in our series of three papers. This is called A Proof of the Field's Conjectures, kind of the thing promised in the title. And this is joint with Satoshi Murai and Andy Wilson. I'm doing something a little bit different for this talk. I have notes that are kind of partially prepared, and I'm going to fill certain things in. This is largely because some of the methods involved in this final analysis of what will be the module structure of the superspace coinvariant ring are going to be sort of parabolic generalizations or refinements, if you will, of things that we did previously. So there are a lot of indices, there are a lot of formulas, and I didn't want to sort of take so much time writing them all down. Uh, Also, I think it's maybe somehow bad manners to end a lecture series with a lot of very complicated formulas. So I would like to devote at least part of my final lecture next week to new directions, conjectures, places where kind of this business of superspace or differential coinvariant theory is perhaps going. Okay. So last time we used the theory of hyperplane arrangements and Solomon-Terral algebras to prove the Sagan-Swanson basis conjecture. And let's just recall what was going on there. If I have a subset J of the integers between 1 and n, we have the associated lazy staircase that looks like this. And we can think about the set of monomials in the x variables alone, right, that fit below this lazy staircase. And we had this very important polynomial, f sub j, and it looks something like this. You have a product over indices in your set of x sub little j times a product of, well, differences corresponding to subsequent factors, essentially. And the theorem was that this set MJ, this set descends to a basis of S modulo this colon ideal, I colon Fj, where I is the classical coinvariant ideal. So this theorem is purely a theorem of commutative algebra, no theta variables here, and we proved it not using Gröbner theory. We don't know a Gröbner theoretic proof. We don't know an elementary proof, but this was really using short exact sequences that really were coming from hyperplane arrangements. And as a corollary of this theorem and our sort of Gröbner leading term analysis from like Andy's lectures, we were able to show that if you kind of glom these m sub j's together by multiplying them by theta monomials and taking a disjoint union, you get a set of monomials m, and we could prove the Sagan-Swanson basis conjecture that m descends to a vector space basis of SR. So before I go further, are there any questions about where we were? The vector space structure. Okay. And I'm aware that this format might make me go a little bit faster, so if I'm going too fast, just shout out, interrupt me. Okay, so our goal today is to obtain a formula for the bigraded character, right? The bigraded Frobenius image of SR, right? And this bigraded character is going to be described combinatorially in terms of the following symmetric function. So this is a symmetric function in the usual infinite set x, x1, x2, x3 variables involving an additional parameter q. It's indexed by two integers, k less than or equal to n, and it's called c and k xq. And there are various ways to define this symmetric function. I could give it to you in terms of delta operators. I could write down a Schur expansion. I could write down something with Hall-Littlewood polynomials. But I'm going to give a combinatorial definition that's actually equivalent to the thing that Andy talked about on the first day. And I'll define these terms in a minute. This C and K is a sum over all ordered multiset partition sigma of size n with k blocks of an x weight corresponding to sigma, and q, your parameter, raised to a statistic called the number of inversions of sigma. So let me immediately retreat to an example. So what's an ordered multiset partition? So an ordered multiset partition is nothing more than an ordered list of non-empty sets of positive integers. So you can have overall repetition of integers, but if you'll notice, you have no repetition of integers within these three sets. And sort of by convention, you write these things in positive order. N, the size, is the total number of integers that you see. So actually, let me write this over here. So here n is 1, 2, 3, 4, 5, 6, 7, 8. And k is 3, that's the number of blocks. And we have an x weight, and the x weight is, well, what you might expect. You just record the content, right? So I see one copy of 1, I have an x1. I see one copy of 2, I have an x2. I see two copies of 3, I have an x3 squared. I see two copies of 4, I have an x4 squared. I see a 5, and I see a 6. So this is the x weight. This would be x sigma. And then I have q to some mystery inversion power. So how do we talk about inversions in ordered multiset partitions? Well, they're a lot like inversions and permutations. We're going to look for out of order pairs, but now with the proviso that the smallest, or smaller, sorry, entry in an out of order pair has to be smallest in its block. So let's do this. I guess the 2 and the 1, they're out of order. The 3 and the 1 are out of order. The 3 and the 5 are out of order. And you might say, well, it looks like the 5 and the 4 are out of order, but because the 4 is not minimal in its block, that does not contribute an inversion in this sense. Okay, so I have kind of three inversions like that. And what other inversions do I get? Well, I guess the 5 is out of order with 3. 3 is minimal in its block, so that's okay. And then also, I think the 4 is out of order with the 3. And those are all the inversions I can find, and there are 5 of them. So here I have q to the 5th. So this combinatorial object contributes this particular monomial to C, I guess, 8, 3, x, q. So it's fairly clear that this is a quasi-symmetric function. It's less clear, but it can be shown that it is in fact a symmetric function, and it is also less clear, but it can be shown that this is in fact sure positive. Okay, so questions about C and KXQ. All right. So our goal is to prove the following formula. So we're looking at this bigraded SN module SR, and it has an X grading and a theta grading, and I'm going to track my X grading with Q and my theta grading with Z. And the goal is to prove that the bigraded Frobenius image of SR is equal to the sum as k goes from 1 to n of z to the m minus k, this exterior grading tracker, times c and kxq. So this is the bigraded character, and you might also be interested in, are there more combinatorial results if we coarsen the grading? And yes, there are. So as Andy explained very well, the ungraded character of SR is isomorphic to the sign twist of the permutation action of Sn on ordered set partitions of n. And furthermore, if I focused on just the exterior degree n minus k part of SR, what I get is the sign twist of the permutation action on ordered set partitions of n having precisely k blocks. So this was kind of all explained the first time, but I think it's good to remember it. And in fact, to achieve this goal, we're going to do all of these things at once. Sometimes in this business, if you're analyzing a graded or a bi-graded SN module, you prove an ungraded statement like this or like this somehow at first using a technique like perhaps orbit harmonics. But these techniques are not really so available or are available in such a nice way in the superspace ring. And consequently, we're actually just going to prove the bigraded character, and these other things are going to be corollaries. Okay. So the overarching principle that we're going to use to kind of analyze bigraded characters is really just this kind of general idea from symmetric function theory and SN representation theory. So if I have a partition mu of n with parts mu1, mu2, and so on, we have this Young subgroup S mu of Sn, and this is S mu1 cross S mu2 cross S mu3 and so on, sitting naturally inside Sn. And I'm going to write epsilon mu for the symmetric group algebra element that anti-symmetrizes with respect to S mu. So I'm not anti-symmetrizing probably with respect to the full symmetric group, but on the other hand, I am with respect to S mu itself. And we have this wonderful fact. If V is an SN module that we really want to understand, well, maybe we want to understand, its Frobenius image, right? The symmetric function that we get by replacing every irrep V lambda with the corresponding Schur function S lambda. And knowing that symmetric function is the same as knowing V up to isomorphism. So how can we hope to understand the symmetric function? Well, we can pair it using the Hall inner product with an element from a basis. And I am going to use the E basis here. So the pairing of E mu with the Frobenius image of V is equal to the vector space dimension of epsilon mu applied to V. So epsilon mu, this linear combination of permutations, is an operator from V to V. I look at its image, that's a subspace of V. I take the dimension, and this dimension is equal to this inner product. So this is true, I should say, for all partitions mu of n. So if I knew all of these dimensions, I would therefore know all of these inner products, and because the E's form a basis and the Hall inner product is an inner product, I would therefore know this Frobenius image, right? So that's a very useful principle if you want to study SN modules, right? And just for emphasis, because we'll be thinking about not just SN modules, but bigraded SN modules, if you have a bigraded module, V, and if you want to understand now the bigraded Frobenius image of V, and we're going to imagine that V, like SR itself, has two gradings, bosonic, fermionic, if you like. Well, again, I can understand this thing by pairing it with all possible elementary symmetric motions. And this pairing is going to be the bigraded Hilbert series of epsilon mu V in Q and Z. Really, there's not really any added information in this second bullet point. I'm just looking at things bigrading by bigrading. Okay, so we're going to try to consider, for the case of V equals SR, a way to sort of get at what this bigraded Hilbert series is. And we're going to start with a very sort of general observation. So we have a basis. We have exactly one basis, actually, of the superspace coinvariant ring SR. This is the Sagan-Swanson monomial basis M. And if I have a basis of an SN module, And if I just look at what I get by applying epsilon mu to M for all monomials M in my Sagan-Swanson basis, well, what I get is certainly a spanning set, right, of the image of SR by epsilon mu, right? This would be true for any linear operator, including the action of epsilon mu. But this spanning set, is in general almost always going to contain a lot of linear dependencies. And these linear dependencies can be extremely complicated, especially because we're working modulo and ideal. But what we're going to do is we're going to kind of cross our fingers and just eliminate the obvious linear dependencies. And what do I mean by obvious? I'm going to say instances of zero. So if applying epsilon mu kills a Sagan-Swanson monomial, it doesn't need to be in any basis. It couldn't be in any basis. And also, I'll say duplicates up to, well, I could say something like non-zero scalar multiple, but in this context, it's actually just going to be sign, right? So if I have one instance of a polynomial that I get by anti-symmetrizing and another instance of that same polynomial, I only need one, and I even only need one up to sign. So these are sort of easy linear dependencies. I'm not thinking about things like what happens modulo my ideal. So if I kind of trim down this spanning set with these obvious linear dependencies, I still get a spanning set. And I want to introduce really some of the combinatorics for analyzing this kind of trimming process. So we're going to be defining signed partitions. Really, I would have preferred to call these superpartitions, but unfortunately, the term superpartition is already in use, and it means something confusingly different. So this was about the best I could think of. So a signed partition, we have our kind of partition mu, and we're going to think about a sequence gamma of non-negative integers which are sandwiched between the zero sequence and mu. So 0 is less than or equal to gamma I is less than or equal to mu I for all I. And I'm going to have some pictures that go with my signed partition. So here, n is 15, and here's a partition mu of 15, 744. And gamma, this sort of signing or enhancement, is 403. So, these numbers kind of sit between 0 and the corresponding values in mu. And what I'll do is I'll write the numbers between 1 and n in a line here. So 1, 2, 3, 4 up to 15. And I'll draw some bars corresponding to the parts of mu. So I'm kind of separating out the first 7 numbers, the next 4 numbers, and the next 4 numbers. And I'm going to put some red underlines like this under the suffixes of the things in these batches, where the number of red lines in a given batch is the size of the corresponding part of gamma. So I have 4 red lines here, 0 red lines here, and 3 red lines here. Okay, so a combinatorial way of sort of looking at these signed partitions. So I'm just drawing the same picture for this example and a little bit of terminology. I'm going to associate a set, and think of this as a lazy staircase set, associated to any signed partition, and this will be the set of underlined numbers, J mu gamma. So J mu gamma in this case will be 4, 5, 6, 7, 13, 14, 15. And finally, we want to get something algebraic. I should think about some sort of monomials. So M mu gamma will be the set of monomials in the x variables which satisfy the following properties. So they're going to satisfy this Sagan-Swanson condition of living below the J mu gamma staircase. And within each segment, we're going to have strict increase for the things without red underlines under them, and weak increase for the things with red underlines under them. So let's look at what this means in our running example. So here we have the same signed partition, and I just wrote its staircase. So the red underlines are telling you where the staircase is lazy. The staircase informally is kind of given gamma. It's as active. It's being lazy as possible. It's being lazy as late as possible within each segment. And this is what the staircase looks like. And what conditions do we have on these monomials? So first off, the exponent ai is less than the ith thing in this staircase for all I. And then we're going to have some strict increase conditions and weak increase conditions. So starting with the first segment, I guess we'll have A1 less than A2 less than A3 because those are not underlined. And then still in the first segment, we'll have A4 less than or equal to A5 less than or equal to A6 less than or equal to A7. And there's no relationship between A3 and A4. In the next segment, we'll have a 8 less than A9 less than A10 less than A11. And then in the final segment, well, there's no relation on A12, but we'll have A13 less than or equal to A14 less than or equal to A15. Okay, so these are monomials in the x variables that satisfy this kind of below a lazy staircase condition that we've been looking at before, but we have these additional weak and strict inequalities. And the observation to make is that if I were to look at the union over all gamma, sandwiched between 0 and mu, so all possible sort of signings of my partition, of the following set of superspace elements. So I'll take a monomial in m mu gamma, I'll multiply it by the corresponding set of theta variables, and I'll mu antisymmetrize. What I get will be a spanning set of epsilon mu SRN. And really, why is this true? This is following from, I'll just say, eliminate obvious, where obvious means what I said previously, linear dependencies from the set of superspace elements obtained by applying epsilon mu to the Sagan-Swanson monomial basis. Somehow, applying epsilon mu is saying that, well, within each of these segments, I can sort of put all the theta monomials at the end. And furthermore, I'm going to die, right, if any two non-thetaed things are equal. So I can assume strict increase among all non-thetaed indices and weak increase along thetaed indices. And furthermore, you might say, well, what if I had red underlines occurring earlier in this sequence? What about monomials coming from there? Well, those monomials sort of didn't have the same opportunity in their non-theta indices to sort of be all they could be, right? So somehow we're making the lazy staircase a little bit taller by pushing these theta indices to the end. So this observation takes a little bit of thought, but it can be shown. So questions about this? All right, so we've got our spanning set, and the conclusion that we can draw from this is I can find an upper bound on this Hilbert series. So this Hilbert series has upper bound given by the sum over 0 less than or equal to gamma less than or equal to mu of z to the size of gamma, the number of underlying things, times the sum over m in m mu gamma q to the degree of m, just kind of counting things by degrees. Okay, so we have an upper bound like that, and we are ultimately going to want to show that it's an equality. So before we really launch into doing that, we should talk a little bit about the analysis of symmetric functions, right? Because we want to talk about bigraded Frobenius images. So, um, as a matter of fact, this symmetric function I said was the thing that we want to ultimately show is the bigraded Frobenius image of SRN, and we want to look at its pairing with the typical E mu. And this inner product, this pairing, is the same thing as the bigraded generating function by degree of monomials that I showed you before. So like we had this kind of Hilbert series upper bound here given by counting these polynomials really by bosonic fermionic degree, and we have the exact same combinatorial thing here. Now, why might something like this be true? Well, we have a different proof in our paper that's algebraic, but there's actually kind of a combinatorial way to see it. So there's a result of mine joint with Jim Haglund and Mark Shimizono that says what happens when you take C and K and you apply EJ perp. This is the adjoint with respect to the Hall inner product of the operator given by multiplication by EJ. And what you get is a sum that looks something like this. So it's a sum as r goes from 0 to j of q to the r choose 2. I have a couple of q binomial coefficients, and then I have c sub n minus j, comma k minus r, so kind of smaller c functions. And the way that you can prove this, the way that we proved this in our paper, this was our kind of second joint paper, something like sure delta operators at t equals 0. Um, the way that you prove this is with the IMV expansion that I showed you before of C and K. And if you sort of think about how monomials in M gamma mu are defined, we have these strict increase and weak increase conditions. You can sort of think about this first thing as corresponding to a strict increase condition, right? Kind of counting monomials that have to strictly increase by degree, whereas this thing is a little bit more like a weak increase condition, sort of a Q binomial, Q multinomial. And if you were to apply this recursion with the fact, together with the fact that E mu perp is E mu 1 perp, E mu 2 perp, and so on, you would obtain this fact, right? So our overall goal is to show that this graded Frobenius image, right, is equal to this symmetric function, and it will follow if we could only somehow prove that the vector space dimension of epsilon mu SR is greater than or equal to, we want to bound from below now, the sum over 0 less than or equal to gamma less than or equal to mu of the size, the number of monomials n, m mu gamma. Right? If we could show that this dimensional inequality is true, well, we have the other dimensional inequality, so we have to have a dimension equality, and furthermore, this would force a Hilbert series equality here, right? So we would get this Hilbert series equality, and it would coincide with this thing here, and we would show that the bigraded Frobenius image of SR is equal to that. Okay, so we're kind of down to really what was the last domino to fall in this project, bounding the vector space dimension of epsilon mu SR from below. So any questions about this? Okay, so the way that we bounded just the Hilbert series of SR from below was using inverse systems. And we're going to do the same thing here. And we're going to use this fact about inverse systems that if I have an ideal that's stable under the action of some group, the corresponding quotient ring is isomorphic as a graded module, not just a graded vector space, to the corresponding inverse system. And in particular, SI perp is isomorphic as a bigraded SN module to SR. So therefore, the vector space dimension of epsilon mu SR is equal to the vector space dimension of epsilon mu SI perp. So we're going to switch over to the inverse system, and we're going to show that this vector space dimension is at least this combinatorial quantity. Okay. So if I'm going to do this, if I want to kind of understand this vector space epsilon mu SI perp, I kind of need some tools. I need some initial elements that I know live in this vector space, and I need some operations under which this vector space is closed. So let's write these down. So if I have a partition mu of n, the vector space epsilon mu SI perp, first off contains the usual van der Waals. So we know that the van der Waals is in SI perp, and the van der Waals is antisymmetric with respect to all of Sn, and therefore in particular with respect to S mu. That's fine. So it contains delta. It's also closed under the action of these higher Euler operators. So remember that dj applied to a superspace element F is the sum as I goes from 1 to n of partial jf partial xi to the j theta I. So here, j should be bigger than or equal to 1. And well, this is true because these dj operators are equivariant with respect to Sn and therefore preserve the antisymmetric property with respect to S mu. And now this third property, well, in the context of mu equals 1 to the n, the kind of where if I turn off the parabolic subgroup, I would just say I'm closed under differentiation with respect to the x variables, but that's actually not true anymore. Here I'm going to write is closed under a more restricted set of operations, namely the partial differentiation action of S mu. So this is the set of S mu invariants inside S. So it's a set of maybe F and S. Whoops. Let me do this a little bit smaller. F and S such that W F equal F for all W in S mu. So I'm no longer allowed to take arbitrary x derivatives. I'm only allowed to take x derivatives that live inside the mu invariants, right? So not quite as many tools to work with. And we're going to use these tools to build kind of fancier looking versions of those D operators. And they're going to construct some helpful elements of the inverse system for us. So here's a horrible definition, but don't worry, we will have an example, okay? So if I have a signed partition mu gamma, where mu and gamma both have k parts, we're going to look at something called a translation sequence, capital T or boldface T. And a translation sequence is a set of k sets, T1, T2 up to Tk, where each Ti is a subset of the ith batch of numbers determined by mu, and this subset has to have size gamma I. And every Ti is going to determine a partition UIT, which I'll define by example. It's basically measuring how far this translation sequence translates or shifts away from maximality. And we're also going to have a polynomial weight for a translation sequence, which will be a certain product of Schur polynomials. So let's immediately have an example. So here we have n equals 15, and I have a partition mu of 15, 7, 5, 3, and I've divided the numbers between 1 and 15 into blocks of sizes 7, 5, and 3, like that. And I have assigning gamma, which is 4, 1, 2. So we have these red underlines, and I see 4 red underlines in the first block, 1 in the second, and 2 in the third, like that. And what I'm going to do is imagine that, these red underlines, it's kind of like my life. I was born in Michigan, I moved to California. They're moving westward, right? But there are these, I don't know, international barriers or something. They can't cross the international barriers. These blue squiggles are where they ended up. And these blue squiggles, the sets of positions occupied by the blue squiggles, are going to be the entries in the corresponding sets of the translation sequence. The translation sequence here is sets T1, T2, T3, where T1 is 2, 3, 5, 6, T2 is 8, and T3 is 13, 15. So we're going to associate a partition to each of these subsets. And the number of parts of this partition, if you are willing to accept 0 as being a possible part of a partition, they're going to encode, well, how far did each of these elements translate? So this first element translated, I guess 2 over, right? He jumped like from here to here. So the first part of this partition, u1, will be 2. This second element also translated 2 over. This second part is also 2. This third element translated 1 over. This third part is 1. And this fourth element translated 1 over. This fourth part is 1. So I guess this guy was kind of ambitious. He went all the way he could. That's 4. And this person moved over 1. And this fellow stayed at home. So 0. And if you think about the partitions that you can get this way, kind of within any given interval, you'll have partitions that fit inside a box, right? That's kind of another way to kind of think about the possibilities. And I'm going to define a polynomial weight, and as suggested by this S underline notation, this will be a product of Schur polynomials. So my first Schur polynomial will be an S2, 2, 1, 1, but in what variable set? Well, these things kind of remember where they came from. I'm going to take the last variables, the last 4 variables in this case, inside the corresponding interval. So I'll have x4, x5, x6, and x7. Then I multiply by the thing for the next interval. I have an S4 in the single variable x12, otherwise known as x12 to the 4th power. And then I have my last interval. I have an S10 in the variable set x14, x15, otherwise known as x14 plus x15. So that's the weight associated to this translation sequence. Sorry that it's kind of a lot of notations. These weights are going to be important in our inverse system analysis. And now I'm going to define fancy D operators, and what we'll be doing is very kind of similar to the usual D operators, but now with the new data of mu, gamma, and translation sequences. So once again, we're going to be looking at various matrices, and these matrices are going to contain both the x variables we had before, but also some new commuting variables, y1, y2, and so on. So y1, y2 are going to be new commuting variables. And to let mu be a partition of n, and for r less than or equal to n, we're going to define the mu power matrix P in our mu in the y variables. And here's what it looks like for n equals 7, r equals 3, and mu equal 3, 2, 2. And you'll notice that if you kind of have a photographic memory from my earlier talk, this is the same as the power matrix from before, right? I just have y1 powers, y2 powers, y3 powers in the first, second, and third rows. And the powers are kind of inversely proportional, if you like, to the column position. And the only difference here is for psychological reasons, I am putting these red bars corresponding to the parts of mu. And if everything is mu segmented in this parabolic story. So next up, we're going to define the mu factor matrix. And here's where things get a little bit interesting. So I wrote down sort of some words up here, but maybe it's better just to immediately look at an example. So n is 7, r is 3, and mu is 3, 2, 2. And I'll have this r by n, so a 3 by 7 mu factor matrix that looks like this. And I have these funny like f super mu sub j polynomials in x comma yi. And well, what do these polynomials actually look like? Well, let's see. So for example, what does this entry here look like? Well, it's going to be something involving y1 and all of the x variables. So I am 2 away from this bar. So this polynomial is going to start with a y1 squared. It's going to be kind of a product of linear factors. And then I'm going to include differences, y1 minus x4, y1 minus x5, y1 minus x6, y1 minus x7 of y1 with all of the x variables that appear after the current block. Okay. And maybe it would be good to do another one of these, right? So here I am 3 away, so I have a y1 cubed, y1 minus x4, y1 minus x5, y1 minus x6, y1 minus x7. And what the heck, one more. So here, still have a y1 because I'm in the first row. These would be y2s if I was in the second row. Now I'm just at the boundary, so I just have y1, but I have to look after the current block. So I have, y1 minus x6, y1 minus x7, like that. So for reasons which I hope you appreciate, I'm not writing out the full matrix because that would be sort of impossible to write these polynomials out in their full glory. But hopefully you see the pattern, and well, maybe just one more. In this last block, we just have things like, y1 squared. And if you're kind of wondering, well, why do I have these powers of y1 now, or y2 or y3? Think bialternate formula for Schur polynomials. Remember, we had those Schur polynomial weights? Ultimately, these powers are going to kind of enter into the bialternate formula. Okay, so we have the f. And here we have an observation that relates the power matrix and the factor matrix. So we had a similar kind of observation in the case of mu equals 1 to the n from before. And the observation is if mu is a partition of n, there exists a lower triangular n by n matrix I'll call C mu, with ones in the diagonal, and entries that are polynomials in the x variables, which are S mu invariant, such that this matrix equation holds. And this really is not anything fancy, right? If you were to think about what would happen if you take this polynomial or this polynomial and expand in terms of the x variables, you would get various powers of y. But because I'm going block by block, right, what I'm going to get in terms of the coefficients of y is automatically going to be invariant with respect to S mu, right? So that's kind of worth thinking about a little bit, but that's really roughly all this observation is saying. And well, what does that mean? If I have a lower triangular matrix with ones on the main diagonal, this means that the determinant has to be 1. And furthermore, my matrix, even if I'm working over a ring like S or even the S mu invariance inside S, I get a matrix which is invertible over S S mu. Okay, so when mu was 1 to the n, this really was what was happening before, and this is just sort of a parabolic enhancement. So now we have the translation sequences coming in. So let's say I have my partition mu, I have my signing gamma, and I have a translation sequence for mu and gamma like this. Well, my translation sequence is a list of sets, and I'm going to look at this matrix ET, which records, well, it's an echelon matrix, a 0, 1 echelon matrix, and the pivots, right, are the things that are not in my translation sequence. So this translation sequence does not contain 2, 4, 5, 7, and those are the pivots. And we're going to just define H mu t to be ET times C mu inverse, right? So this is an n minus r by n matrix over, happy I forgot to write this down because it's important, this ring of partially symmetric polynomials, right? And in some sense, the very last thing that happened in this project was me desperately trying to invert this matrix without realizing that it was a matrix inversion problem. I was trying to write down these crazy differential operators without knowing that this business of, oh, I can invert a matrix really lets me encode these in a much nicer way. And what are these differential operators? I should say nicer ways. So this formula will look very beautiful if you spend several weeks kind of trying to produce inverse system elements. But I understand it might be complicated at first. So we're going to have our signed partition, U gamma, and we'll let T be a translation sequence, and we'll assume that gamma has size R. So the parabolic D operator is an operator on superspace that looks like D mu T. And if I apply it to F, well, what I get is a formula that's very kind of similar to the last time. So what I have is you take F, you sum over all subsets U of the integers between 1 and n of size m minus r. You apply a sequence of D operators to F corresponding to the complement and reversal of U. So then you apply as a differential operator the U minor, the U maximal minor of this kind of mysterious H mu T matrix, and you multiply by a sign and you add, right? So if mu was 1 to the n, this would be the same formula as before. So this is the parabolic D operator. And what are the most important properties of these parabolic D operators? Well, first and foremost, if I apply a parabolic D operator to the Vandermonde, what I get lives inside the vector space I want to study, epsilon mu si perp. And why is that? Well, think about it. If F was the Vandermonde, I know the Vandermonde is an epsilon mu si perp. That was my first fact. Whenever I apply D operators to things in epsilon mu si perp, I stay in epsilon mu si perp. That was the second part of my fact. And if I apply even the craziest possible minor of some matrix that's defined over these partially symmetric polynomials as differential operators, well, I stay in epsilon mu si perp, right? So this is a formula that might look very crazy at first, but it sort of keeps you inside the vector space that you want to study. Secondly, for reasons very similar to reasons in the non-parabolic case, the coefficient of theta k in dt mu delta, sorry, is 0 unless k is less than or equal to in the Gale order of j mu gamma. And this really follows from properties of the determinant. So you can sort of look at what happens if you extract the coefficient of theta k in this. You can write it down as an n by n determinant, thinking about this sum as corresponding to a cofactor like expansion. You apply the fact that C mu has determinant 1, you have a determinant involving factor matrices, and by a support condition, you see that this determinant will vanish unless you have this Gale comparability. And furthermore, the coefficient of this sort of critical theta monomial is up to sign given by the following object. It's going to be given by this product of Schur polynomials times f j mu gamma applied to delta as a differential operator. And here I'll just say, y is 3 true. Determinantal manipulations. So you're going to have essentially a block diagonal determinant plus the bi-alternate formula for Schur polynomials. So I don't really know that it's a spectator sport to look at these manipulations, but what I'll say is that those products, those powers of y variables that we saw in the factor matrix, oops. Oh. So these sort of y variable powers, when you plug in x variables for them to evaluate that theta coefficient, what you're going to get will be this sort of bi-alternate numerator. And the Vandermonde factors in the denominator will come from appropriate parts of this f here. Okay, so this is sort of good news. We have a whole bunch of elements of this vector space that we want to study, and we can use these elements to bound the dimension of this vector space from below. So it's the same overall philosophy, just a little bit more complicated. And the way we're going to do this is as follows. So I'm going to let R mu gamma be this kind of crazy thing. So we're going to look at the quotient of S by this colon ideal, I colon j mu gamma. It's a commutative object. And we'll look at the S mu submodule of this thing generated by these polynomial weights coming from translation sequences. And why is that a good idea? Well, look back at this fact, right? We have triangularity. And if I look at the critical part of triangularity, I have this Vandermonde that generates the inverse sequence for inverse system for I, that's Steinberg's theorem. I'm multiplying, or applying as a differential operator, rather, f j mu gamma, so that gives me a colon ideal. And then I'm thinking about, well, these particular translation sequences, right? So I'm kind of keeping these like that. So we're going to look at this S mu submodule, and what we have, sort of by general algebraic principles, is that the vector space dimension of this module is greater than or equal to the sum over 0, less than or equal to gamma, less than or equal to mu, of the vector space dimension of this module. So from 10,000 feet, what we did was we replaced a problem in supercommutative algebra with a problem in commutative algebra, and we're adding. And what we're going to do is we're going to show that for each particular signed partition mu gamma, this vector space dimension is bigger than or equal to, well, the number of, well, you might say anti-symmetrized appropriately, Sagan-Swanson monomials, right? So we'll show that each of these terms is bigger than or equal to the number of monomials in M mu gamma. And that's going to give us the appropriate dimensional inequality here, term by term. And how are we going to do this? We're going to find a set E mu gamma S of polynomials so that first off, the number of polynomials in E mu gamma is the size of M mu gamma. Okay, and furthermore, we want to show that E mu gamma descends to a linearly independent subset of S modulo I colon F J mu gamma. So we're going to prove this particular dimensional inequality by producing a linearly independent set of the appropriate size. So how do we do that? Well, yet another combinatorial construction. So again, another example. So here we have n equals 11, u equals 443, gamma 122. And we have a translation sequence T, and we have these three partitions coming from my translation sequence 2, 1, 1, 1, 0. And this translation sequence is going to contribute a whole bunch of polynomials to E mu gamma. And what are these polynomials going to be? It's going to be sort of like you choose one from column A, one from column B, one from column C, and multiply them together. So each segment will contribute some polynomials. And the polynomials from the first segment are going to be a little bit boring. So it's actually just going to be the Schur polynomial S2 in this last variable x4. So this is kind of the contribution from the first segment. And by the way, if this translation sequence had made it all the way to San Diego, if it had gone all the way west, there would be no polynomials contributed, and I'll kind of explain why at the end. So this second segment is a little more interesting. So we're going to have a Schur polynomial, S11, in the last two variables. So think about that as kind of coming from the weight. And then we're going to have some elementary symmetric polynomials in all of the variables, namely x5, x6, x7, x8, appearing in the second segment. And these elementary symmetric polynomials will correspond to partitions living inside rectangles. And what are the dimensions of my rectangles? Well, the first dimension is always the number of variables here. So I see 4 variables here. So my rectangle is going to have a width 4. And to get the height, what I'm going to do is I'm going to look at whether there's a blue squiggle under this last entry. So there's no blue squiggle. So I take the corresponding staircase term, which is 4. No blue squiggle means subtract 1. 4 minus 1 is 3. And then I'm going to do something similar for the last guy. I'll have an S10 in x10 and x11 times E lambda 3 and x9, x10, x11. And lambda 3 is going to sit inside, well, I had 3 variables. Blue squiggle under variable means I subtract 2, right? So blue squiggle at the end means I take 6, I subtract 2. What I get is 4. So I take a polynomial from the first set, a polynomial from the second set, a polynomial from the third set, and multiply them together. Okay. So it can be shown by a miraculous identity of binomial coefficients that the number of polynomials that you get this way for all translation sequences is the same as the number of these anti-symmetrized monomials. And another amazing fact is that if you think about what would happen if you multiplied these things out into x variables, what you would get for any monomial that appears always lives below this staircase. And that's basically because these Schur polynomials, well, there's, some bounds having to do with semi-standard flow about how big exponents can be here. And there are also some bounds about what happens when you multiply by these elementary symmetric polynomials. And what's that going to mean? Well, this is some pretty good news, right? Because we had this basis coming from hyperplane arrangement theory of S modulo these colon ideals. So I had this problem of showing E mu lambda, sorry, E mu gamma is linearly independent in this quotient that might make you break out in hives. These are very complicated polynomials. But if every monomial appearing in a polynomial in E mu gamma lives inside, right, this monomial basis, all I have to show is this kind of simpler problem that E mu gamma is linearly independent in S. So we are at 10:01. I went 1 minute over, so I will end on a cliffhanger. How do we show that this crazy set E mu gamma polynomials is linearly independent in S? So what I'll do next time, I'll show this. It's going to be easier. And I will use this result to derive the Fields conjectures, and then I will go into, new directions, new conjectures related to co-invariant theory of differential forms. So a lot of technical stuff. Sorry about that, but it should get more pleasant next week. Thank you.
Hey, very good. Great, great talk. And any questions for Brendan? No? Okay. Well, thanks much, and we'll see you on Tuesday.
See you.
Yeah.
Bye.
So long.